Electrical continuity at service equipment must be assured at all points. This means that all metallic parts of the electrical system must be electrically connected together to form a continuous path back to the source. The purpose of electrical continuity is to provide a low impedance path for fault current to flow, which will allow the overcurrent protective device, such as a circuit breaker or fuse, to quickly trip and de-energize the circuit, preventing electrical shock or fire. Ensuring electrical continuity is crucial for electrical safety. Without proper continuity, fault current may not be able to effectively return to the source, causing dangerous voltage potential on equipment and increasing the risk of electric shock. The grounded conductor, often referred to as the neutral, plays a critical role in establishing electrical continuity within the electrical system. It serves as the primary return path for unbalanced currents in a three-phase system and provides a reference point for voltage measurements. Bonding involves connecting all non-current carrying metal parts of the electrical system together to create a low impedance path. This includes metal enclosures, conduits, and equipment frames. The bonding connections help to equalize the voltage potential between these metal parts, reducing the risk of electric shock if a fault occurs. Grounding refers to connecting the electrical system to the earth. This is typically done by connecting the grounded conductor to a grounding electrode, such as a ground rod or a metal water pipe. Grounding provides a path for fault current to flow back to the source through the earth, helping to trip the overcurrent protective device. Several methods and components are used to achieve electrical continuity. These include bonding jumpers, grounding electrodes, and proper installation techniques. Bonding jumpers are used to connect different sections of metal conduit or equipment together to ensure continuity. Grounding electrodes provide a connection to the earth, allowing fault current to flow back to the source. Proper installation techniques such as tightening connections and using appropriate hardware are essential for maintaining electrical continuity over time. The National Electrical Code, or NEC, provides detailed requirements for electrical continuity in Article 250. This article covers grounding and bonding requirements for electrical systems, including the size and type of grounding and bonding conductors, as well as the methods for connecting them. Compliance with the NEC is essential for ensuring electrical safety. Regular inspection and testing are necessary to verify electrical continuity. This can be done using a multimeter or a continuity tester. A multimeter can be used to measure the resistance between different points in the electrical system. A low resistance reading indicates good continuity. A continuity tester can be used to check for a continuous path between 2 points. If the tester beeps or lights up, it indicates that there is continuity. Firstly, visual inspection of all grounding and bonding connections can be performed to identify any loose or corroded connections. Secondly, perform continuity tests on all grounding and bonding conductors to verify that they are properly connected and providing a low impedance path for fault current. Thirdly, check the grounding electrode system to ensure that it is properly installed and providing a connection to the earth. Fourthly, verify that all equipment is properly grounded and bonded. Fifthly, ensure that all connections are tight and free of corrosion. Sixthly, document all inspection and testing results. There are several common problems that can affect electrical continuity, including loose connections, corrosion, and damaged conductors. Loose connections can increase the resistance of the circuit, reducing the effectiveness of the grounding and bonding system. Corrosion can also increase resistance and weaken connections. Damaged conductors can interrupt the flow of current and compromise electrical continuity. These problems must be addressed promptly to maintain electrical safety. Poor electrical continuity can lead to several hazards, including electric shock, fire, and equipment damage. If a fault occurs and there is poor electrical continuity, the fault current may not be able to flow back to the source quickly enough to trip the overcurrent protective device. This can cause the voltage potential on equipment to rise, increasing the risk of electric shock. Fault currents can also generate heat, which can lead to fire. Additionally, poor electrical continuity can damage sensitive electronic equipment. Maintaining electrical continuity is an ongoing process that requires regular attention. By following the recommendations outlined here, it is possible to help ensure the safety and reliability of electrical systems. Regular inspection, testing, and maintenance are essential for preventing problems and maintaining electrical continuity over time. The importance of grounding and bonding cannot be overstated. These practices are essential for protecting people and property from electrical hazards. By following the NEC requirements and implementing proper grounding and bonding techniques, it is possible to significantly reduce the risk of electrical shock, fire, and equipment damage. Properly sized grounding and bonding conductors are vital for effective electrical continuity. The NEC provides tables and guidelines for determining the appropriate size of these conductors based on the size of the electrical service and the type of equipment being grounded or bonded. Using undersized conductors can compromise the effectiveness of the grounding and bonding system. Grounding electrode conductors connect the electrical system to a grounding electrode. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Bonding jumpers are used to connect different metal parts of the electrical system together. The size of the bonding jumper is determined by the size of the circuit conductors. Ensuring that all grounding and bonding conductors are properly sized is essential for providing a low impedance path for fault current. Many different types of grounding electrodes exist, including ground rods, ground plates, and metal water pipes. Ground rods are typically made of copper or galvanized steel and are driven into the earth. Ground plates are buried in the earth. Metal water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet. The type of grounding electrode used will depend on the soil conditions and local requirements. The resistance of the grounding electrode system should be as low as possible, ideally less than 25 ohms. This can be achieved by using multiple grounding electrodes or by improving the soil conductivity. The location of the grounding electrode is also important. It should be located as close as possible to the service entrance and should be protected from damage. Electrical metallic tubing, or IMP, rigid metal conduit, or RMC, and flexible metal conduit, or FMC, are commonly used to protect electrical conductors. These metal conduits can also serve as grounding conductors, provided that they are properly installed and connected. E&T is a thin-walled steel conduit that is easy to bend and install. RMC is a thick-walled steel conduit that provides excellent protection for electrical conductors. FMC is a flexible metal conduit that is used in applications where flexibility is required. When using metal conduits as grounding conductors, it is important to ensure that all connections are tight and that the conduit is properly bonded to the equipment being grounded. Non-metallic conduit, such as PVC, cannot be used as a grounding conductor. In these cases, a separate grounding conductor must be installed. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. They work by monitoring the current flowing in the circuit and detecting any imbalance. If a ground fault occurs, the GFCI will quickly trip, interrupting the flow of current and preventing electric shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. They are an important safety device that can help to prevent electrical injuries. Arc fault circuit interrupters, or RFCIs, are designed to protect against fires caused by arcing faults. Arcing faults can occur when damaged or deteriorated wiring creates a high-resistance connection. This can generate heat and ignite nearby materials. RFCIs work by detecting the unique characteristics of arcing faults and tripping the circuit breaker before a fire can start. RFCIs are required in many locations, such as bedrooms and living rooms. They are an important safety device that can help to prevent electrical fires. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other events. SPD work by diverting the surge current away from the protected equipment. SPD are available in a variety of types and sizes. They can be installed at the service entrance or at individual pieces of equipment. SPD are an important investment for protecting sensitive electronic equipment. Regular maintenance is essential for ensuring the continued effectiveness of grounding and bonding systems. This includes inspecting connections, testing continuity, and replacing damaged components. A qualified electrician should perform regular maintenance to ensure that the system is functioning properly. Proper documentation is also important. This includes keeping records of all inspections, tests, and repairs. Documentation can help to identify potential problems and track the performance of the grounding and bonding system over time. When making changes to an electrical system, it is important to ensure that the grounding and bonding system is properly maintained. This may require adding additional grounding or bonding conductors or upgrading existing components. A qualified electrician should be consulted to ensure that all changes are made in accordance with the NEC and local requirements. Electrical safety is everyone's responsibility. By following the recommendations outlined here and working with qualified electricians, it is possible to help ensure the safety and reliability of electrical systems. The principles of electrical continuity are fundamental to electrical safety. A solid understanding of these principles is essential for anyone who works with electricity. Remember that electricity can be dangerous, and it is important to take precautions to protect yourself and others from electrical hazards.